Good morning, everyone. Welcome back to Math 220. So just a reminder of things on the agenda as I've been writing them here. We have a quiz on Friday on Chapter 2. So the way that'll work is I'll spend the first part of our class period on Friday answering questions that come in from Katie. Probably that will be the majority of what I will do on Friday. So if questions come up between now and then, I'll answer those before the quiz. Then I'll give you a PDF of the quiz and let you take an hour or so to hand it back to me via Katie. So that's the plan for Friday. Don't forget that the homework for 2.2 and 2.3 is due tomorrow. So please, hopefully you've looked at it already and viewed the videos and that sort of thing. And so I expect there'll probably be some questions about that today. But just in case you have missed that, make sure you keep that in mind. And so that is both section 2.2 and 2.3. Speaking of, I did return your LaTeX homework with comments. So for some of you, I either said, okay, this is perfect, or these are the things to fix. And you'll see I'll do that for some homeworks through this course. If there's something that's important that I don't want you to miss, I'll often just hand it back to you and make you redo it instead of giving you a grade if it's missing some important component of the material. So I'm going to start by going over the Katie questions today. That's agenda item 1. Then I have prepared some questions to practice with the sorts of skills we've been working on, but I will ask if anyone has any more questions that come up as I go over these questions from Katie. And I did want to remind people, they've been slowly trickling in, but don't forget to put a question on Katie. I'm just keeping track. You get a point for each question you put on Katie. Well, you get a point for your first question on Katie for each class, so don't forget to do that. All right. So let's go through the Katie questions now. Okay, so my first question is about A is 3 and B is 2, 6. It is about A intersect B. And so A intersect B in this instance is the things that are in both of these sets. So that would, in this case, end up being that. So if you think about this on a number line, here is 1, here's 2, here's 3, here's 6. And so if I put A up here, A is the numbers between 1 and 3, like that. And if I put B down below it, B is the numbers starting here and going over to 6. So the numbers that are in both are the numbers including 2, because 2 is in both, but excluding 3, because 3 is not in A. And so that's why you get this sort of half open, half closed interval as the answer. Please remember, whenever someone is using interval notation, these things are talking about real numbers, not integers. So this is not the set 2, 3, 4, 5, 6. This includes numbers like pi and e and all that jazz in the middle. Questions about any of that? Okay. Next question was about the difference between A minus B and B minus A. So A minus B, this is things in A that are not in B. And this is things in B that are not in A. Okay. So maybe to spell that out in terms of symbols, if x is in A minus B, that just literally means x is in A and x is not in B. Okay. Whereas x is in B minus A means x is in B and x is not in A. Okay. So in particular, here's one big difference. A minus B, this is a subset of A. And B minus A is a subset of B. But then A minus B has trivial intersection with B. And has trivial intersection with, remember, means the intersection is the empty set. And likewise, B minus A has trivial intersection with A. An additional way of thinking about that is in terms of these Venn diagrams. So if I have sets A and B, then A minus B is this piece. But B minus A is this piece. Okay, so for the other things, A intersect B and A union B, it does not matter what order you write them in. So A intersect B is the same thing as B intersect A. A union B is the same thing as B union A. But for set difference, it actually matters which is which. That is the point of this. The next question I have is about the proof box I put at the end of proofs. So this is called a proof box. This is the sort of more modern tradition, is to write a box at the end of a proof to indicate that the proof is done. You'll often see in very, very old things, you'll see people write QED, which is short for quod erat demonstratum, which is what was to be shown in Latin. But this is like 50 years old, plus people don't usually write that. People now usually draw a box. You can really use any symbol that you like. In fact, LaTeX will let you set what the proof box symbol you use is. But when you are writing a proof in LaTeX, if you just use the begin proof environment, where you put your proof in the middle, it will automatically draw some sort of box at the end. But if you would prefer to have your proof box be a Batman symbol or whatever, you are more than welcome to do that. Some people in the past have had fun finding what the most obscure symbol in LaTeX is to use as their proof box. But I think generally in any mathematical writing, I think you should definitely have a symbol to mark that your proof is over. You will find if you're reading a math textbook and they don't do that, it becomes much, much harder to read. Another question is about when to use there exist versus there exists. Okay. So exists and exist, this is actually just the conjugation of the verb exist. So this is a distinction between singular and plural. So this is for plural things, this is for singular things. Okay, so there exists X in A such that blah, blah, blah. There exists Y in R such that blah, blah, blah. If I'm talking about the existence of a single thing, I use there exists. Whereas if I'm talking about the existence of multiple things, there exists X, Y, and Z in R such that blah, 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 then I'll use there exist. So where I'm underlining the lack of an S there. That is the distinction between there exist and there exists. This is not a super important distinction, but that is why I vary which one I use. Okay. Next up is about the negation of greater than and greater than or equal to and less than or equal to. Okay, so let's write for here x in the reals, and let's write down what is the negation of x is greater than or equal to 7, x is greater than 7, x is less than or equal to 7, and x is less than 7. Okay, so if x is a real number and it's not greater than or equal to 7, okay, again, you can think of this all in terms of a number line where there's really sort of 3 pieces on the number line. There's 7 numbers bigger than 7 and numbers less than 7. And so whenever you're taking a negation, you're saying, okay, I know it's not, okay, and so if x is greater than or equal to 7, you're saying, I know it's not 7 and it's not greater than 7, so the negation here is x is less than 7. Okay. Whereas if all I know is that x is not greater than 7, then I'm excluding this bucket. And so then that means it could be in either of these buckets, so that gives me x is less than or equal to 7. Okay. Likewise here, if x is not less than or equal to 7, then it's not one of those two, so then that means x is greater than 7. And then if x is less than 7, well, sorry, if x is not less than 7, then x is greater than or equal to 7. Okay. So your goal when you're writing down a statement and its negation is you want to sort of mop up all the possibilities. So if I've included 7 here, I need to exclude 7 here. If I've excluded 7 here, I need to include it there. Okay. Remember, between a statement and its negation, exactly one of them is always true. It's worth noting, when you're talking about integers, things get a little bit weirder. And why is that? If I'm talking about integers, if I draw my number line here, 7, 8, 9, 6, 5, 4, and so on. If I say that x is greater than 7, I'm really saying I'm talking about these numbers over here. And so with integers, x is greater than 7 means the same thing as x is greater than or equal to 8. Okay. Again, this is for integers. And so what that means is, because you could write x is greater than 7 or x is greater than or equal to 8 and have them mean exactly the same thing, when it comes to writing the negation, you could write the negation here either as x is less than or equal to 7, or, and this is an or as in this is another solution, you could write the same thing as x is strictly less than 8. Okay. Again, this is when the x that you're talking about is inside the integers. And so this fact that there are these large gaps between integers means that when we think about integers and talk about statements between them, things are going to end up being a little bit different, and so you'll see this trick often ends up coming up. Okay, questions about that so far? I next have a question about negating unions and intersections. So let's just write out, first of all, what does x is in A union B mean? This means x is in A or x is in B. So if you then negate x is in A union B, you can do that by following our negation formula. And so this means x is not in A and x is not in B. Okay, note the or becomes an and. And then how does that differ from intersections? If I write down what it means to say that x is in A intersect B, that means x is in A and x is in B. So the negation of that, which I guess I've been writing like that, I've read it the other way there, so the negation here would become x is not in A or x is not in B. Okay. Someone asked about bipartitions, which is a question from the homework, which I will answer after I answer the other questions. If I forget, remind me, and I will answer it. But I wanted to finish answering the conceptual questions first. So next, someone asks, how does cardinality work for sets that have sets as elements? Which is a good question. So here is a sample horrible set. that has an element that's not a set, an element that is a set, and an element that's a set that contains sets. But the way I described that just told you the answer, which is that this is one element, this is another element, and this is a third element. And so the cardinality of this set is just 3. So the cardinality here is just counting the number of objects in the set. And the fact that the objects in this case are themselves sets that contain other objects, the cardinality doesn't see that. So the cardinality counts this just the same as it counts a single one. Okay. Next, someone asks about the distinction, if any, between for all and for every. And this is purely an aesthetic choice. These are functionally equivalent. So you might, for example, deliberately vary them just to keep the reading not unpleasant. Again, if you use the same word over and over and over again, just like in a Paideia paper or whatever, it gets really grating to read. In the same way, if you're writing proofs or mathematical texts in general, you usually want to just vary saying the same thing in slightly different ways just to keep it sort of having the right texture of something that sort of sounds, I don't know, poetic is maybe a reach, but something that sounds like spoken English, so to speak. So the next question is about the various ways of writing sets. So here I've just taken n and z plus. And so before I go ahead and fill this in, think to yourself, what kind of thing would go in each of these blanks? So what kind of thing would go in this blank, and what kind of thing would go in the second blank? Okay, this is a good audience participation moment. What's something that could go in the first blank? Right. So this could be the set of n and z plus such that n equals 3. Okay. Now, if I happen to write the set of n and z plus such that n equals 3, what set have I just described? Right. I have now described the set 3. Okay. So most of the time, probably, I would have written this instead of that. But not always. There can be various reasons why you end up writing a set that's a really complicated-looking way of describing a simpler thing. But the other example in chat is also great, which is this thing is just some descriptor. So this could be something like such that n is prime. Perfect. I'm looking here in the second slot. I'm looking for a description or a condition. if you wanted to use the sort of formal language, you'd say here I'm looking for a statement about n. Okay. Where, remember, a statement is just something that is true or false, and so I am looking for something about n that is true or false, and then this is collecting all of the ones where that thing is true. For the second one, what kind of thing would I put here? What is an example of something I could put in the second blank? To n, right. So here I'm looking for something that is really a formula. Yeah, so 2n or n squared plus 3 are both great examples. This is a formula to be evaluated at n. And so if I wrote down this set, I have really described a set that I could equally well have described in this other way. So let's take this set. This is the set of n in z plus such that what? Well, this set here should be 2 times 1, which is 2, 2 times 2, which is 4, 2 times 3, which is 6, and so on down the line. What is the property that describes these things here? Right, this is the set of n and z plus such that n is even. Right. So this is a good sort of Rosetta Stone to keep in mind. This set is exactly the same thing as the set of 2 times n, where n is in z plus. This is just the same set written in each notation. Kratib, you wrote 2n is in z plus. That's almost right. I think it's really n over 2 is in z plus, I think is really the thing you're looking for. Okay. And again, I think the reason why these things are easy to confuse is that they're written in exactly the same way, even though they mean something completely different. And in particular, this vertical slash that gets used in both is really a completely different English word. So if I were to read this, I would say this is the set of n in the positive integer such that n is even. So this bar is a such that. Whereas I would read this as the set of 2 times n for n in z plus. So I would read this as the word for. And so it is definitely very understandable to take a bit to really fully internalize both of these ways of describing sets, but they'll both come up a lot. Okay, any questions about that? Okay, and so I promised I would talk about this bipartition question. If you've not looked at it yet, this is question 7 on the homework. Okay, and so it says this. Okay, so here is the definition. And so the thing we're defining here is a bipartition of a set S. And so what am I looking for when I describe a bipartition of a set S? Well, I'm really looking for two sets whose union is S, but that have no elements in common. So let's write down, say, a bipartition. Let's write down a bipartition of the reals. Okay. So I want two subsets of the reals whose union is all of the reals, and which have no elements in common. Okay. One way to do this is to just pick an A first. So let's say I pick A to be the interval -1, 1. Okay. So I just picked that out of thin air. So then what does B have to be if my A is the interval -1 to 1? Exactly. So I want -∞, -1, bracket, union, bracket 1, infinity, parenthesis. Okay. Namely, again, I want the union of these two things to give me all of the reals, and I want the two of them to have nothing in common. Okay. And so really what I've described here, this B, this is really the complement of A within the real numbers. And so then what is our bipartition? Our bipartition here is actually the set -1, 1, comma, -∞, -1, union, 1, infinity. What's the cardinality of this bipartition? Right. Its cardinality is 2, right? This is a set with 2 elements. It just so happens that both of the elements are themselves sets that have infinitely many elements. But this bipartition, like in fact every bipartition, has 2 elements. Now there's one wrinkle here I want to point out that becomes relevant, which is this is a set, which means the order doesn't matter. And so what that means is if instead of starting with a equals the interval from -1 to 1, if instead I had started with a being this thing that eventually ended up being b, then b would have ended up being -1, 1, and I'd have ended up with the bipartition that, which is just this, but in the other order. But remember, sets don't have orders. And so, in particular, what that tells you is that these 2 bipartitions are actually the same. But that's what a bipartition is, and that's what this definition says. I'm taking some set, whatever set I start with, and I'm splitting it into 2 pieces where every element is in one piece and there aren't any extra elements floating around. Any questions about that, or any other questions from the homework, or other questions that have arisen in our discussion today? You can take a screenshot and crop it and just show me the input output to Wolfram Alpha or whatever to show me that you knew what you were checking. Sorry, I didn't say the question. The question was, for one of the homework questions, I specifically asked you to use a computer to check something because it involves large numbers. And student asked, what was it that I wanted you to show in the homework? And I said, you could just take a screenshot of the input and output of the computer for that particular thing. Okay, so let me put up some examples. Okay, so let's start with some set stuff. So for each of these sets, I want you to write down a couple of elements. Okay, let me give you a minute to think about these, and then we can talk about these questions. Okay. So we want to write down some sample elements here. So this is the one where this thing is a formula, and I am going to plug n's in from the positive integers into that formula. So I could plug in, say, 3, in which case I would get 3 factorial plus 1, which is 7. I could plug in 1, in which case I'd get 1 factorial plus 1, which is 2. If I plugged in 2, I'd get 3, and so on. So 2 and 7 would be examples of elements, but you may have found other elements. Okay. B is perhaps more interesting. What are some examples of elements of B? Ah, yes, and this is a good question, because people in the chat have said both 25, 121, and 4 and 5. Which are the things that are actually in the set? Okay. And the things that are actually in the set are the n's. So 4 and 5, and I'll let you check 7 also works. These are in the set. Okay. And 4 is in the set because 4 factorial plus 1 is 25. Okay. 5 is in the set because 5 factorial plus 1 is 121. Okay, and these are perfect squares. Okay. And so the things in the set, though, those are the n's. Okay. Interesting side note, as far as anyone knows, these are the only 3 integers that are in this set. But there could be others, no one knows. Okay, what about C? What are some examples of things in C? Or in the set in part C, I suppose I should say. 41. Okay, why is 41 in this set? What are x and y? Four and 5, right. So 41 is in the set in C because we can choose x is 4 and y is 5. Okay, and 4 squared plus 5 squared is 41. Now, note here we're only looking at p's that are at least as big as 20, so you might start just trying things and you might figure out, okay, well, I'll look at, well, 21's not prime, I guess 20's not prime, 21's not prime, 22's not prime. And then you get to 23 and you think, okay, 23's prime. But then when you try and look at 23, it turns out if you look at the statement, it turns out if you look at this statement that this statement's actually false. There are no such x and y. Okay, and so then you have to keep going, and you have to say, okay, well, what about 24? No, that's not prime. 25, that's not prime. 26, it's not prime. 27, it's not prime. 28, it's not prime. And you maybe try 29. Okay. Do there exist x and y and z plus such that x squared plus y squared is 29? Yep, 2 and 5. So 29 is also in this set. And so it's in the set because it's prime, and it can be written, as May says, as 2 squared plus 5 squared. Okay. And so again, you then maybe keep going and try 31. Unfortunately, there are no such things for 31 either. And so this is why this takes a bit, because you have to find the primes, and then once you find the primes, you have to decide if you can actually write them this way or not. And so the first ones you can find are 29, 37, and 41. And so these are the first few that will happen to show up in this set. Are there any questions about this set notation? Okay, let me write down some statements, and I'd like you to practice negating them. Okay, and I'll give you a couple minutes to look at these and practice, and then we'll talk about them. Okay, so these questions can end up being trickier than you'd think because we sort of talked about all the basic logical operators and how to negate all of them. But then often it turns out that the things we write down without thinking about it often aren't spelled out super explicitly in terms of those logical operators. And so in order to negate them, we actually need to think carefully about what the thing that's written down actually says so that we can figure out how to negate it. Okay. So the first one has the form if P then Q. What's the negation of if P then Q? P and not Q, right. So the negation here is P and not Q. Okay. Now I want to emphasize we're going to negate this if-then statement. And then in the next example, I'm going to ask you to write down contrapositives of some if-then statements. And those are very different things. Okay. So if someone asks you to negate an if-then statement, then you're going to get P and not Q. And if someone asks you to take the contrapositive, then you're going to write down this not Q implies not P business. Make sure you don't confuse these, because in fact, logically, they're about as opposite as possible. Because remember, the contrapositive, the whole point is that it's equivalent to the original implication. Okay, so let's write down the negation here. So P and not Q. Okay, so in particular, we leave this piece completely alone. So it reads, if P is 10 to the 700th, sorry, no if. We just leave this piece completely alone. P is 10 to the 700th plus 7 is prime. And now we negate this piece. Okay. So here's the first instance where we have to take a moment to sort of decipher what the words written here actually mean. Namely, so is P plus 10 or P minus 10. This is sort of English way of saying, so then P plus 10 is prime or P minus 10 is prime. Okay. So I have to then negate that. And so that becomes P plus 10 is not prime. this or becomes an and. Okay, so we have the if part and then the negation of the then part as our negation of the if-then statement. Okay, questions about that? Okay, so next up, we have this statement. And so you'll see in math, there are an awful lot of for every there exists type statements. And so remember, we learned that if you negate a for every statement, you get a there exists statement. Okay. And so this for every x in R, that negates to there exists x in R. And as soon as we have a there exists, we pick up a such that. Okay. And then likewise, the there exists flips to a for every. Okay. And then the such that goes away because the such that was there was pairing with the for every. And so I'll write we have, again, just to put some space between this and an equation. And now here is the part where it's really, really easy to write something that is utter nonsense. Namely, when someone asks you to negate n is less than or equal to x is less than n plus 1, it is really easy to write down that. But if someone really asks you to interpret what mathematically is it saying about x, if I write this down, this is pretty nonsensical, right? So if n was 4, this would be saying 4 is less than or equal to x is less than 5. And so now this would be saying 4 is greater than x is greater than or equal to 5. This doesn't really actually make sense. And so in order to even negate n less than or equal to x less than n plus 1, I have to first decide what this actually means. Okay. Namely, what does n is less than or equal to x is less than n plus 1, what does that mean if I want to write it in terms of our logical operators that we've been using? Right. This is really an and statement. This thing is really saying n is less than or equal to x, and x is less than n plus 1. Okay. So this negation is really... So when I go to do this negation, I'm really negating n is less than or equal to x, and x is less than n plus 1. Okay. And now this negation I know how to do. Namely, this negation is going to be n is greater than x, or x is greater than or equal to n plus 1. And so that will give me the correct negation of this original statement that I wrote down and then covered up. Sorry about that. So be super careful, and in particular, read the thing you wrote down afterwards, and make sure the thing you wrote down as the negation is something that actually makes sense. Because if the thing you write down as the negation doesn't actually make sense, well, then it can't possibly be right. Just to note, there's a slightly different way you could view this, which is that if you wanted to think about this in terms of the number line, what I'm saying about x, when I say n is less than or equal to x is less than n plus 1, is that x lives in this shaded piece. And so then the negation of saying x lives in this shaded piece is that x lives somewhere else. And the somewhere else in particular includes the greater than or equal to n plus 1 piece, which is that one, and includes the less than n piece, which is that one. Okay, great. Questions about any of that? Okay, last up here we have another if-then statement. And this one, because of this and, is really tempting you to try and negate this piece, because this would negate really nicely. But remember, the negation of an if-then statement does not involve negating the if part, so that I just copy. Okay, and then I negate the then part, so that there exist becomes for every. And so here I really want for every string of consecutive integers x, y, z, w. And so then we have x plus y plus z plus w is not equal to n. And you'll see here I did a little bit of bending in terms of what word choices I made just to try and make this read more naturally. And I swapped the equals to a not equals, but put it in the other order because I'm now making a statement about x, y, z, and w. And so you don't have to do that. You could write it in the other order. This is just what felt most natural to me. Okay. Let me give you some statements to write down the contrapositive of. And just a reminder, the contrapositive of an implication P implies Q is this thing not Q implies not P. Okay. So again, take a couple minutes, just take a stab at these. Again, you'll really help yourself if you write these down, because you want to be making as many mistakes as you can on things that aren't going to be turned in. Okay, let's take a look at these. So first up, we have if f of x is differentiable, then it's continuous. Okay. So we want if the negation of this piece. But note, I should definitely not write if it is not continuous, because here I have to interpret what this it is telling me. Namely, the it here is referring to f of x. So when I go to write the contrapositive here, I have to write if f of x is not continuous. Okay. Or totally fine if you prefer discontinuous. And so then when you go to write this, you need to write the negation this. Then f of x is not differentiable. Okay. Or you could have replaced this f of x with an it if you really wanted to mimic the wording of the original as much as possible. Okay, so now here I want to negate at least one of x, y, z, and w is odd. What is the negation of at least one of x, y, z, and w is odd? All of them are even, right? Okay. Again, you can think of this in terms of the possibilities. How many of x, y, z, and w could be odd? Well, 0, 1, 2, 3, or 4 of them. Right. At least one applies to 1, 2, 3, or 4 of them are odd. So then the complement of that is 0 of them are odd, but 0 of them are odd is the same thing as saying all of them are even. Or, if you want to think about it a different way, saying at least one of x, y, z, and w is odd is a sort of concise way of saying x is odd, or y is odd, or z is odd, or w is odd. Okay. It is really that four-tuple or statement. And so if you negate that four-tuple or statement, you get x is even, and y is even, and z is even, and w is even. So however you go about it exactly, you should get to this piece as the negation of the then part. Then, and so now x plus y plus z plus w is even. Okay, the point of this next one is that you don't need to know what the words mean in order to negate it. So, sorry, you don't need to know what the words mean in order to negate it or to write down the contrapositive or whatever. Why didn't you include at least? Because the opposite of at least one is none. And so when I negated at least one, I got to none of these things are odd, which is the same as saying all of these things are even. Does that make sense? Okay. So when I go to write down this one, I'll write down if S is not compact, then, and now I have to negate S is closed and bounded. So I will get S is not closed. Or, because the and becomes an or, S is not bounded. Oops. Okay. Okay, and this last one is worded a bit awkwardly to start with, but that's not going to stop us from writing the contrapositive. So I have to negate not both of x and y are rational. So the opposite of not both are rational is both are rational. Okay, and note the both there is extraneous. I could say if both x and y are rational, it would mean the same thing as if x and y are rational. And again, this is really a preview of why we're doing this, because next week we're going to be writing down proofs of statements of this sort. And it turns out to be way easier to write down a proof of this statement, the one in black, than of the one in blue. Okay. So we're going to see that it's quite often useful to replace the thing you're trying to prove with its contrapositive, and that's again just as good because the contrapositive is logically equivalent to the original implication. Okay. I have one last example, and by the way, these examples cover everything, or all the styles of questions that appear on the quiz. This last example, I have a variety of statements here for you, and I would like you to decide which of these statements are true. I will again give you a minute to think about it. talk about these 5 statements, and let's decide whether we believe they are true. So this first statement is that for every x in the real numbers, there exists a y in the real numbers such that x equals y squared. Okay. And remember, if I'm saying this whole statement is true, I'm saying that I can plug any x from R I want to into this part I've underlined in blue, and it will be a true statement. So for example, if I plug in x equals 7, I would get the statement that there exists a y in R such that 7 is y squared. Now, not asking about the original, but just this x equals 7 statement, is this true or false? This is true, right. Are there any problem x's where I could put this in and get a statement that wasn't true? Yeah, negative numbers. So if I plugged in, say, x equals -4, this would say there exists there exists y in R such that -4 equals y squared. Okay. But that's definitely not true because I can't square a real number and get a negative number, so this is false. Okay. And so then, because this is a for every statement that is not true for every element of the set, namely it's not true for x equals -4, this whole thing ends up being false. Okay, again, the only way a for every statement can be true is if every single statement you spit out of it by plugging in values in your set ends up being true. Okay. Are there questions about that? I know processing these takes some getting used to. Okay. Now, these next two have exactly the same words, but in a different order. So here I have for every x and z, there exists a y, versus here I flipped the quantifiers. Okay. That certainly should raise some suspicions that maybe one of these is going to work and one of them is not going to work, which is exactly right. One of these is true and one of them isn't. Which is true, the first one or the second one? The first one, correct. So the first one is again saying put in whatever x you like. And so put in x is, say, 65. And then I would get the statement that there exists y in z such that x plus y is greater than 189. And certainly there does. Namely, I could take, say, a million, and it would be true that a million plus 65, sorry, this x is supposed to be 65. That was the whole point. I could pick, for example, y equals a million, and it would definitely be true that 65 plus a million would be greater than 189. Okay, so this one is true. Okay, but even if I chose some ridiculous number like negative 1729, it's still true that there exists y and z such that negative 1729 plus y is greater than 189. Now, we'll work on next week how exactly to write a precise proof of this, but this is in fact something that works for every x you can put in here. No matter what x you pick, you could always find a y. Okay. So this one, in fact, is true. Okay. Now, again, I want to emphasize, what's the difference between these two? What does it change that I moved the there exists piece before the for every piece? Okay. And what it changes is that now, since the there exists piece comes first, when I write this down, I'm claiming I can choose a y that works for every x. Okay. So in this first one, there were many y's, because for each x, I could custom fit a y to work for that x. And that was because the for every x came first. Okay. Here, we're only allowed to choose one y. But even if I chose a ginormous y, like let's say I chose y to be a billion, okay, then what would this say? Well, if I chose y to be a billion, 10 to the 9th, this would then say that for every x in z, x plus a billion is greater than 189. Okay. And while assuredly this is true for quite a few x's in z, it's not true for all x's in z. Right? This is false. Okay. Because, for example, I could take x to be negative 10 billion, and then this won't be true. Okay. So in this instance, there is no y, no single y that works for every x. Okay. Is one of the last two true? Right. The answer to is one of these last two true is no. These are both false. Right. So So I think this first one looks really plausible. How many elements are there if I put A and B together? Well, you take the number of elements that were in A and the number of elements in B, and you're off to the races. The problem with this one, though, is that A and B can overlap. So, for example, if A is 1, 2, 3, and B is 3, 4, 5, then A has 3 elements and B has 3 elements. So the size of A plus the size of B would be 6. But if I take the union of these two, it does not have 6 elements. It only has 5. Right? And this, again, is just a repeat of the fact that sets don't have multiplicities. And so once 3 is in the set, unioning on another 3 doesn't do anything. There is no such thing as putting an extra 3 into a set. Okay. And so this, what I've written down here, is really a counterexample, which is something that we're going to talk about at great length next time. For the last part, what this is really saying is the intersection of two sets strictly smaller than both of the sets? And it doesn't have to be, because, for example, I could choose A and B to be equal. So let's say I choose A to be 1, 2, 3, and B to be 1, 2, 3. Well, if I chose A to be 1, 2, 3 and B to be 1, 2, 3, then the size of the intersection is 3. But the minimum of the sizes of these two is 3, and 3 is not strictly less than 3. This would, in fact, be true if I replace the strictly less with a less than or equal to. All right. That's all I have for you today. If you can make sure you get all of that, you should be well prepared for the quiz on Friday. Once you get all the homework done, I recommend you start viewing the stuff for next week. So I've already started posting the Chapter 3 stuff, which is what we're going to talk about in week 2. So you can keep ahead and start thinking about that. I'll post the homework for next week soon as well. That's it for class for today, but I do have office hours now, so if you want to hang around and if you have any questions you want to ask, go for it. I'll be happy to stick around for a while and answer any questions that come up. But if not, have a wonderful afternoon, and I will see you on Friday. I can. Okay, so the negation of P if and only if Q is P XOR Q. Okay, so remember, P if and only if Q means that either P and Q are both true or both false. This really says they have the same truth value. Whereas XOR Exactly means the opposite. It means they have opposite truth values. And so these two are negations of each other. Let me know in the chat if there's other questions. I suppose you can write that. The question is if this is a valid thing. But if you did, and if you accepted it, which I don't see any reason why you wouldn't accept it, but it would be another way to write the set 3, right? Because here we're saying plug every natural number into the formula 3, uh, which is just going to give you, well, 3. So I don't think there's anything wrong with it, but I think you probably wouldn't see it very often. Yeah, so I think you're saying something like that. And yeah, you're right. This is the empty set. It has no elements. It's perfectly valid, though. Nothing wrong with this construction. But probably actually the worst part of this whole set builder notation is that it's very easy to write down a set where it is not at all clear whether it's actually empty or not. Thomas, that is because mathematically, open and closed aren't opposites. Uh, Sets can be both open and closed, or neither open nor closed. So you just have to write not closed. Uh, that is just a poorly chosen linguistic thing. I think I made a note about this in one of the videos. Be careful about guessing what the negation of a math word that you don't know is. But if it is an unfamiliar word, I'm not going to complain if you just write not closed, uh, for example. Yeah, I mean, that's certainly not a big deal. It's well beyond the scope of the course, so I wouldn't complain over much. But yeah, that's why I wrote it that way. I will post a PDF to Katie and then put a spot for you to turn it in. So you will do the quiz in LaTeX and then hand me virtually a PDF. So it will be roughly similar to the review we did today, but you'll just type up your answers to each of them and then turn them into the slot on Katie. Let me have a look at that. So in 2.2 number 5, it's given you specific sets in A and for A and B, so you should be able to write these things as intervals. No problem, I understand the I would not know what to write if it did not say that, so that was why I had to look at it real quick. Yes, absolutely. Interval notation is okay and encouraged. All right, folks, let me know if there's any last-minute questions. And if not, I do have office hours tomorrow, so feel free to stop by then. But if I don't get any questions in the next couple minutes, I'm going to shut this down for the day.